Welcome, and thank you for joining this webinar. From Connectivity to Understanding, the Semantic Future of AI Communications, prepared by the Alpert Research Team. Understanding semantic communication, or SEMCOM, is a strict strategic imperative. It literally represents the foundational shift required for the networks of the 2030s. Let's look at the network architecture. If I'm a major operator, how do I actually implement this? Do I just rip out the classic OSI model that has governed the internet for decades? Does the entire protocol stack just go in the garbage overnight?
No, it's absolutely not a rip and replace scenario. You can't break the internet to upgrade it. It involves building parallel planes. The literature defines a specific three-layer SEMnet architecture that sits alongside traditional systems.
Layer 1 is the cognitive sensing layer. What's interesting here is that it doesn't just passively collect data like a traditional antenna. It actively infers user intent and uses generative AI to constantly discover new knowledge in the environment.
Then you move up to layer 2, which is the semantic transmission layer. This is the engine room. This executes the deep JSCC we discussed earlier. It maps the features to latent tensors, formats them, and physically routes them over the air interface.
And finally, layer 3 is the control and application layer. This is the management suite. It handles the knowledge-based synchronization we just talked about. It orchestrates tasks based on intent and manages network slicing.
This architecture is what completely transforms telecom carriers. They are evolving from being utility providers of dumb connectivity pipes into operators of intelligent information platforms.
So when a telecom engineer looks at a diagram of the 6G stack, what does this actually look like functionally?
Strategically, it manifests as the introduction of the semantic intelligence, or SI plane. In current 5G networks, we have the user plane, which carries your streaming video, and the control plane, which carries the signaling data to keep the network running.
Okay.
In 6G, the SI plane runs parallel to them, acting as the cognitive, AI-driven engine of the entire network.
If the SI plane is running the show, if the semantic noise gets too high, what is the backup?
There is always a hard-coded operational fallback. If the semantic link fails, say the confidence score drops too low, or a safety-critical anomaly is detected that the knowledge base doesn't recognize, the system instantly drops the semantic link entirely. It falls back and opens a classical, robust, old-school bit pipe to transmit and verify the raw data pixel by pixel. Furthermore, they deploy software called monitor agents. Their sole job is to log the latent space activations inside the AI so that human engineers can later mathematically audit and explain exactly why the AI made a specific decoding decision.
We aren't completely abandoning the classical bit pipe during the transition. It's a hybrid approach. But as we move into the actual integration with 5G Advanced and 6G, we are seeing AI-native air interfaces starting to replace the handcrafted mathematical waveforms that engineers have used for decades. The networks will literally learn the best way to transmit data based on the specific hardware and environment they are in. To deploy semantic communication at scale, we must examine the evolution of ORAN, the Open Radio Access Network. Historically, building a cellular network meant buying monolithic proprietary equipment. If a telecommunications operator bought a base station from a major vendor, they bought a closed black box. The specialized radio hardware at the top of the tower and the baseband software processing the signals at the bottom were inextricably locked together by proprietary interfaces like CPRI.
You could not mix and match. You couldn't buy a cheap radio antenna from a startup and run it using advanced AI software from Google. You were locked into the vendor's ecosystem.
ORAN shatters that lock-in. It deliberately decouples the hardware from the software. It standardizes the interfaces between the radio unit, the distributed unit, and the centralized unit. This allows operators to use commercial off-the-shelf servers, standard cloud computing hardware to run their radio networks as virtualized software functions.
And the true brain of this new open architecture is a component called the RIC, the RAN Intelligent Controller.
It enables network operators, or even third-party developers, to deploy AI-driven software applications to manage the radio spectrum resources in real time.
As we look towards 6G, the literature introduces an evolution of this concept, the semantic RIC, or SRIC.
In a traditional 5G network scheduler, if 10 users simultaneously request data, the network essentially attempts to divide the physical resource blocks of the spectrum equally.
The SRIC abandons that egalitarian bit-level approach. It allows the network to allocate radio spectrum based on a semantic grade of service.
It executes specialized algorithms known as semantic apps. These apps operate on a sub-millisecond control loop. They analyze the incoming traffic flows and prioritize them not by file size, but by information value and task importance.
Imagine the network scheduling system as a triage nurse in a crowded hospital emergency room. In a traditional network, the triage system operates on a strict first-come, first-served basis. treating every patient exactly the same regardless of their condition.
The traditional network honors the size of the data in the order of arrival, not the severity of the intent.
The semantic RIC transforms the cell tower into a master triage nurse. The SRIC instantly evaluates the semantic intent of the data packets. It sees the massive VR gaming download, registers its low strategic importance, and places it in the waiting room, allocating it lower priority spectrum. Simultaneously, it registers the tiny braking signal from the autonomous card, recognizes the critical information value, and instantly clears a dedicated, interference-free path straight to the operating room. And it manages this complex prioritization autonomously, evaluating thousands of intents per millisecond.
This capability fundamentally alters the monetization strategies for telecommunications operators. For years, operators have struggled to increase their average revenue per user, or ARPU, because they have been relegated to selling dumb pipes. They sell a pool of gigabytes, and the tech hyperscalers, the Googles, Apples, and Metas, capture all the value by running intelligent services over the top.
The SRIC allows operators to reclaim that value. They can begin monetizing the intent. A telecom operator will no longer just bill an enterprise logistics company for the terabytes of data their drone fleet consumes. They will offer a guaranteed service level agreement, an SLA, promising a 99.99% task success rate for collision avoidance.
They transition from selling raw connectivity to selling cognitive services and guaranteed business outcomes. The economic value shifts from the width of the pipe to the AI intelligence orchestrating the traffic within the pipe.
From Claude Shannon's rigid mathematics in the 1940s to the AI native architectures rolling out in the next few years, the core takeaway is clear. Prioritizing the transfer of meaning over the transmission of bits is the absolute cornerstone of the next era of global connectivity.
It's the only way forward.
It is the only mathematical, physical, and economic way we can scale successfully into the 2030s. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their strategic implications. Click the links below to learn more. Thank you for taking this deep dive with us. Keep exploring and keep asking questions about the hidden architecture of our digital world.